So this talk is about extending the field of view for augmented reality devices, and ever since the beginning, one of the first augmented reality devices, such as this device here from Ivan Sutherland, to the most recently yet to be seen, but in some sense announced device, Microsoft HoloLens. The core idea of augmented reality is that it is able to use computer-generated graphics to overlay them onto the real world and to immerse you in a particularly interesting experience where, because there's a tight relationship between the computer-generated graphics and the real world, you have the symbiosis, you have the augmentation of the world, and the graphics seems to coexist. The reality about these experiences right now is that at most that you can hope for to get is something like this. Really, you're going to have a very limited field of view experience. And actually, when you look at the current set of devices that are commercially available for, including the HoloLens in this category, they're all basically hover between 25 and 40 degrees field of view. The device that we'll be using in this research, in this paper, is the Lumos DK32. In some sense, you can say it's the best of breed in terms of the field of view. It's not that different compared to most other devices there. Now, when you compare that to the human visual field of view, and I'm talking about binocular field of view, it extends pretty much 180 degrees or even more left to right horizontally and less vertically. Now, when you plot this, and this is not plotted with distortions, but just kind of for scale, when you plot this and compare this with the augmented reality field of view, you see that you're really having this tunnel vision effect. You're only basically focused on the fovea and a little bit of a parafoveal area of your retina. Of course, even just for comparison, the current state-of-the-art virtual reality devices are about 100 degrees field of view. This is the DK2. So just for comparison, you get a lot more in VR right now than you get in AR. This is how it feels, and I apologize for dark video, but it's hard to shoot directly through the glasses. So this is what it feels if you currently look at the augmented reality scene directly through the lens of a Lumos DK2 display. So why is it hard? Why is it hard to get wide field of view optically see-through HMDs? Well, first of all, most of these solutions, typical solutions, depend on having a beam splitter embedded into an optical waveguide. So you really are stuck in a trade-off. If you really want to have wide field of view, you usually need to increase the thickness of this waveguide, which increases the weight, which increases the complexity, an optical complexity, and oftentimes it greatly increases the costs. And in the same time, you're also having this additional part, increased weight, but also reducing image clarity because you're looking through more glass, looking through more optical elements, and it also, transmissivity of that optical element goes down. So the other hard part about making a wide field of view is that not only do you need to have a wide field of view, but you also actually need to account for the fact that your eyeball rotates in the eye socket, and therefore you need to have multiple, you need to either have multiple eye boxes or a very large eye box to actually account for a wide field of view. So I don't want to pretend that there are no attempts in actually making wide field of view, but they're right now mostly confined to either lab optical benches. So for example, using the freeform optics on the left side, the authors suggest having them tiled to potentially have very wide field of view. Or on the right side, there's a pin light display, which is in essence a light field display, which trades off resolution and clarity for a wide field of view experiences. Now, what we are presenting here is kind of an opposite approach. We're trying to say you can create a wide field of view if you treat the display, the problem as a hybrid display. So we take our Lumos head-worn displays and we combine them with a projector and a depth camera system, with a ProCam system, to create a wide field of view experience. And here's what it looks like. This is the beginning scene that I showed you with just the display. And if you tightly correlate the projection with the display, you can have a full field of view experience that is in essence a hybrid display. It has an inset that you view in the glasses, and as well as periphery that's backfilled with projector. So here you see our display. It's currently tracked with these very attractive trackers. It's an OptiTrack system embedded in the ceiling, but you can pick whatever variety of tracking you would like. And there's a projector and a camera system. We use a Kinect version 2 in addition to a standard projector. Now, what you're really seeing if you're standing over the shoulder to the person is that as you're looking around, you can kind of guess where they're viewing, and the projector is rendering everything in the periphery, and also, in a sense, some stuff in the inset area. So there's a bunch of related work in hybrid displays, including some of Steve's early work on using the HMD to kind of give you extra information around the LCD display. And we've also done a piece that is in essence a hybrid display where we combine projectors with a television set. But what we do differently in FoveAR is that first we combine the HMD and projection, but we explore the complementary nature of the overlapping displays. In essence, we don't treat them as completely separate, as just extending the field of view. We actually explore, and I'll talk about this, we explore the ways that you can combine them for interesting effects. And the second effect is that we really focus tightly on providing dynamic view-dependent experiences, which is what virtual reality and augmented reality are really kind of, that's the forte of those experiences, having the 3D view-dependent experiences. What do I mean by view-dependent for projections is something like this. Now, this is an art piece that is completely static, so if you stand in a particular location, you will get to see this view-dependent scene rendered for you. And as we showed last year, we can now do this at runtime on completely deformable geometry. In other words, we can do this on anything that happens to be in the room, including people that happen to be there. So this is a view that from a paper we presented last year, but we use this exact technology in the FoveAR work this year. So here you see actually this airplane is projected not only on the furniture in the room, which is static, but also on people that just happen to walk into the room. So such experiences are fundamentally, such projected augmented reality experiences are fundamentally monoscopic unless you have shutter glasses and things like that. That, in all honesty, when people view them, they're immersive and they're engaging, but they are a little bit flat, which makes it for great YouTube videos because they look great on video. Also, it's great if you happen to have one eye. So for select few folks, that's fabulous. But for the rest of us, we actually found that both the HMD versions and the projector-based versions are very, very complementary. So here I list a set of qualities that each of them contain, and it's really interesting to see how well they actually complement each other in terms of the capabilities they bring to the table. In particular, I will focus on this last one, which is really interesting. I think it can be exploited, and I'll show you later how we exploit it. But this idea that if you're using projectors to overlay non-view dependent content, that's actually in some sense you're texturing existing surfaces in the environment, surface shading. That is very powerful. It also has extra benefits for not necessarily being tracked because it doesn't depend on any particular viewpoint. So it's perfectly stable in the environment, and it doesn't cause any, it doesn't have any artifacts of jitter or lag or anything like that. And I'll show you how we do that. So before that, we've implemented 4 different FoveAR experiences just to kind of highlight the possibilities. So first one is this idea where hopefully there's some sound, but maybe it's not playing right now. Is there sound? No. Anyway, the idea here is that you have a moving helicopter in the room, and this is an experience that is extremely hard to be actually enjoyed with just an HMD, because the helicopter just goes out of your view all the time. The second one here is just this Rube Goldberg machine where the user can actually explore this animated scene and see different parts. And as well, I'm kind of showing over-the-shoulder views, and as well as views showcased through the experience. This last one, this third one is a virtual telepresence experience. And again, we're having a person recorded, depth recorded at a remote location and then played back to the user. If you did this just in the glasses, it becomes impossible to keep a person's face and facial expressions, as well as what they're talking about, the objects in their hand, in the same view. So you lose the context of the conversation all the time. With projections in the periphery, you get all this contextual information, you keep track of the entire experience, and you still can focus and get the stereoscopic view at the exact location. We also did this little shooting game just for fun, because it's always fun to blow out stuff. So let's talk about rendering. Let's talk about how do we actually get the content in there. We explore 4 different schemes. Actually, that's not true. We explored a lot more, but these 4 are actually the most promising ones. And I'll show each one in detail. The easiest thing to think about is to look at the content between the glasses and in the periphery and just replicate it. So in this case, the glasses are showing exactly the same stuff that the projector is displaying behind. So projector displays a full scene, and the glasses are displaying the same thing. While this is powerful, you kind of see all the problems, and you have some overlap, extra brightness in the glasses view because you're basically compounding the effect. We can also use the Occlusion Shadow, which is an approach that was suggested by Bimber and Froelich before for just projection-based setups, in which case the projector would basically just project the black line. It would create the dark area where the HMD can overlay content. So this is the occlusion shadow. This is how it looks in the environment. But that creates this sharp discontinuities between the on-screen content in the glasses and the projection part. So then we started pushing the envelope a little bit further and saying, well, what if you used each modality to its best capabilities? So in this case, we use all the non-view dependent content and project that back into the scene using the projector. So the textures on the wall here are projected only, and only overlay the 3D content that really needs to stand out from the wall. So we call this a surface shading approach. And here, this is what you view in the scene. And lastly, to make this even slightly better, of course, you can actually feather the experience. So you blend the transition between them to really get rid of all the sharp discontinuities. And this is the one that we mostly prefer. This is the one that all our test users also prefer. All right. So to render FoveAR experiences, we require 5 passes, and I'll just briefly go over why we need 5 passes. For the HMD, you need a left and a right eye. So those are 2 of your passes. For the projection, the way the projection mapping works, you need to first render off-screen what you think that the user should be viewing. And in our case, we have 2 different views there. One for the inset, one for this part that's going to be overlapped by your glasses, and the other one for the wide field of view, the rest of the projection. So that's 2 passes. And then last one is the projection mapping pass, which basically combines all these 2 passes into one distorted view for the projector so that it looks undistorted to you. And let's talk briefly about the design considerations. So the easiest thing to think about this combination is where the projector actually aids the glasses. And in this case, projection gives you a wider field of view. It removes static tracking noise and things like that in there. The other way to think about it is you can think as glasses being assistive modality for the projector. So they add 3D stereo. They add content where you don't have projections, things like that. But most interesting combinations start when you really start thinking about glasses and projection offering complementary context. So public, private, or choose the best display based on suitability. So I'll show you the examples. I also leave HDR in terms of extending the actual display capabilities, kind of as future work potential in this space. So here's an example of, only private content displaying in your glasses, and public ends up being just projected, so for everybody else to see in terms of cards. Or here, when you have content that's close to the existing surface, so when this globe is close to the wall, it ends up being projected only. But when it gets further out, when it starts becoming very stereoscopic and 3D effects take over, we transition them back into the glasses. So in conclusion, the limitations of our approach are currently that we deal with a single projector. So realistically, we only have about 120 degrees horizontal field of view. But we've showed last year, actually Brett, who's going to be giving the next talk, he showed last year how to make the entire room basically projection map. Calibration is challenging. There's a lot of things to calibrate in here, but we've recently released a Room Alive toolkit, which greatly simplifies the idea, the calibration process for calibrating projectors and cameras together. So this is an open source project at this point, and you guys are welcome to try it out and create your own experiences. by doing FoveAR, we really trade off mobility for extended field of view. So some potential is here to actually mount some of the projectors there, or maybe combine them in a different, interesting way, something like what CastR are trying to do right now. There's also obviously some tracking noise in our current experimentation. We don't compensate between the two screens. The HMD is actually much brighter than the projector right now, which is shown in the videos. And lastly, we also really need to figure out which image do you want to project into the projector? Which eye do you want to choose? Because depending on which eye you choose, you're going to have more or less disparity between the projected scene and what's actually viewed in the HMD. So I hope that I've convinced you that combining projectors and HMDs is an interesting potential to really get you a wide field of view AR experience. I just want to thank my collaborators at this point and take some questions. Thank you. I'll leave the slide on the collaborators because they're not standing here, so they need some extra praise. Thanks.
Hi, Evan Suma from USC ICT. So in the VR community, we've studied field of view for quite some time, and one of the things that is really, in that community at least, tends to be routinely ignored is vertical field of view. Mm-hmm. So a lot of the studies tend to really concentrate on horizontal field of view and maximizing that. But we're starting to see that the lower vertical field of view is really important, particularly where you get your horizon line information and your kind of postural stability from. So I was just wondering if you could comment on the vertical field of view and any artifacts or issues you might have run into doing this type of hybrid information, particularly in the lower boundary below your eye line.
Well, I don't have any specific kind of studies or specific findings. For majority of folks, we've actually greatly extended the lower field of view. Just because of the nature of our glasses and how they were, we 3D printed some frames around them. Basically, most of the visibility was to the sides and to the bottom, below the glasses for people, not so much above the glasses. It does definitely create, just like you see in the videos, it does create a very different experience when you can actually see content overlaid almost on the floor, and you get a lot of, especially if you're trying to create an illusion of a larger room or smaller room and things like that, it totally changes the nature of that experience, as you would imagine. Where with the tunnel vision, I think all of those estimates are really difficult. I don't have hard data to do it. I think it would be interesting to kind of follow up. One thing that our test users, so there was a little pilot evaluation that we did, and you can read the results in the paper. But one of the findings was really interesting, is that because we ended up doing the surface blended approach in the surface shaded approach in our blending of content, a lot of the content in the periphery was actually very stable. It did not depend necessarily all of it on the position of the user's head, which self-reported for a lot of folks who had VR experience. They said that, you know, they did not, even though they extended the field of view, they did not observe any simulator sickness, increased simulator sickness parts or anything like that, because of a lot of that stability that you get in the periphery like that. That's a very that's a really good result, given that our tracking and combination between the two displays was left a lot to be desired, let's just say. Yes.
Thank you for the splendid talk. I'm Hrvoje from University of Maryland, College Park. I have a question regarding the resolution difference between the HMD and the projection mapping. So I guess that the HMD rendering is high resolution and the projection mapping might be lower resolution. So I'm wondering whether user can notice the difference between HMD and the projection mapping, and how are you blending the boundary between the foveated region and the non-foveated region?
So that's a good question. I think there's different ways to treat resolution. First of all, I think you're absolutely right in terms of the HMD presents you with a much higher resolution, and by that I mean angular resolution, just what you get per angle degree. But in physical terms, both of them are actually pretty similar resolutions, just spread over a larger part. In terms of blending, we were initially really interested in doing almost per pixel style blending or doing some HDR imaging, so like to give you extra content or to brighten up certain parts of the scene. But our alignment, our current alignment and our current calibration and tracking just made that look a lot more blurry than you would really want to. You really need a very tight correlation between what you see in the HMD and what you are having in projectors. So that at this point remains a future work. But I think it's very promising because you can really go into the HDR experiences in that way in the FoveAR area, in the HMD area.
I got it. Thank you very much.
Thank you. Thanks.